Welcome back to lesson 10 of the advanced series. I'm Chili. And today is going to be I'm hoping for a nice short little lesson here. We're going to keep it chill, we're going to relax, we're going to do some vector math, we're going to work with some triangles, it's going to be good. But first, we need to talk about something here. Wait, let me just undo. Yeah, this is not my first take. I had setbacks, let's say. Fucking explaining this vector shit. It's kind of complicated, let me tell you, man. But we're going to do it. Now, the thing that is bothering me is clockwise and counterclockwise. Those two functions. Let me show you why. Let me illustrate. Let me get a different color. I'm not feeling the red today. So we got a couple of axes, x and y. This is in our screen coordinate system, so y is going to be pointing down. Let's say we got a point here, 0.10, and we want to rotate that clockwise. So we go to our trusty clockwise 90 function here. And what does it tell us? Well, it tells us y is going to be equal to negative x, and x is going to be equal to y. So we do that. We say y is equal to negative x, and x is equal to y. That'll be 0, negative 1. And we put a couple of arrows here to represent vectors. And what the fuck is this bullshit? I ordered a clockwise, and this does not look clockwise to me, friend. Maybe you should learn how to tell time. Don't piss on my leg and tell me it's raining. That is clearly counterclockwise. And yeah, that is counterclockwise because the functions that I had written were generally dependent on your normal Cartesian coordinates in which y is positive going up. And when you flip that, you're going to also change the direction of rotation. So, yeah, this is kind of false advertising. How we're going to change that was we're just going to change this to counterclockwise. We're going to change this to clockwise, and all is forgiven. Now, if we find all references on counterclockwise, we're going to find that it has been used in polyclosed in the collision function to find our normal. So we need to also switch that over to clockwise, which would make more sense in a purely visual kind of spatial sense. So yeah, that was bothering me, and it would be a future place for bad shit to happen. But now it's fixed and we can move on. So last lesson, we figured out how to draw triangles because we wanted what our goal is. Let's just make a thing here. This is our polyclosed. We want to make our polyclosed fat. That's fat with a P. And the way we do that is like this. Let's just see if I can't make half decent straight lines. Oh, I'm doing a pretty good job here. This is the best I've ever done. So we draw our fat lines by breaking it all down into polygons, specifically triangles, and then drawing the triangles. Now, in order to get the vertices for the triangles, we already have these ones on the inside. We need to find these vertices, given these ones. So that, my friends, is the problem that is presented to us. So let's try that. Let's get on that bullshit. I'm going to make a bunch of surfaces. So many surfaces. Not surfaces, I mean layers. You don't even know how many layers I made because it's off the screen. So let's say we've got a situation here. we got 3 points on our poly closed. And we want to find a point Q. Right. Let's see if I can't get a dark gray. Yeah, that's a good one. This is dark gray. Believe it. We want to find a point Q on the outside perimeter of our wall. So how are we going to do that? Well, I mean, you could start drawing lines here and saying, well, I could find this angle here and given these points, and then maybe that would, half that angle would be this angle here. And I don't know this length, but I know this length, and I know that this one is parallel to this one, and maybe I could use like coleslaw, and then maybe I could have a side of, you know, that delicious KFC gravy. I don't know if you have that in the United States, but that shit is awesome. We don't have it here in Japan, and I need my KFC gravy. Anyways, what I'm saying is you could approach this from the point of view of angles and trigonometry, but fuck that bullshit, because that is not the way civilized people would handle this problem. What are we, savages? No, we have vectors, people. So we're going to use our vectors to solve our problems, and we're going to be rich, man. Step 1, use vectors. Step 2, question mark, and then profit. That's how it works. So how are we going to do it? Well, the first thing we're going to find, the first thing we're looking for is we're looking for a vector in the direction of Q. All right. Now we know that this vector is going to be halfway. Fuck, I gotta change layers like you don't even know. I'm gonna change so many layers here, people. So let's say we've got a normal that is normal relative to the line segment P0, P1. And we have another normal, if I can change my layer, that is normal to the line segment P1, P2. So this blue vector, which is in the direction of Q, is going to be, directionally speaking, halfway between these two green normal vectors. So the question is, how do we find this halfway? How do we find a vector that's halfway between two other vectors? Well, if you have two vectors and their lengths are the same, you can do this. Let me just, here we go. Take this vector, make the bums touch. And you take this one, get a little ATM action going here, and lo and behold, if you add your two normals together, let's just get a red here for illustrative purposes, you will get a vector. Well, I mean, my drawing isn't perfect, but well, we'll just fudge it. You'll get a vector here that points halfway between those two vectors in terms of directionality. And then you normalize that vector to get the normal in that direction. So all you got to do is add your normals and then normalize the result. Now, how do we get these normals? I think I've already covered this problem, but I'll cover it again quickly for illustrative purposes. What color I got? Red, not acceptable. We need green for this one. So the first step is you subtract P1 minus P0. That gets you this vector here. Then you're going to want to rotate that vector counterclockwise by 90 degrees, or if you are a civilized person, by pi over 2. And that gets you a vector that is pointing well, perpendicular to the vector between P0 and P1. And finally, all you want to do is, you know, normalize that fucker. So scale it down so its length is 1. And then you've got a normal. And it's also incredibly skinny because of the way I did that. But fuck, man, you can't win them all, can you? So that's how you find your normal. Now, there's one caveat in this, and I don't know if I've discussed it before, but I'm going to discuss it now because it's relevant. And that is that case for finding a vector that points outwards. That case works if your polyclosed is defined with clockwise winding. But if your polyclosed is defined with counterclockwise winding, then this is going to be 0, 1, 2. Your vector is going to be from here to here. And if you rotate that counterclockwise, you're going to be pointing this way. So in order for this to work, you have to have your winding going in the same direction every time. If your winding is going clockwise and you want a normal that points outwards, then you can rotate counterclockwise and you will get that normal. But if your winding is going counterclockwise, then you're going to have to rotate clockwise in order to get a vector that's pointing outwards. And vice versa if you want a vector pointing inwards. So you have to be careful of your winding. You always want your polyclosed to be winding in the same direction. Because if they're winding different directions, then you're going to get different results with the same algorithm. So that's my little PSA for today. Watch your windings, bitches. I'm sorry, that was offensive, and I take it back for now. So we have our we've got our normals. If I can do that, get another one going out this way. And we've got our halfway normal, which is halfway between them. So what's the next step, people? Well, obviously what we're looking for, ultimately what we're looking for is Q. And in order to get Q, we want a vector from P to Q, because then we just add P1 to Q, because then we just add that to P1 and we get Q. So how are we going to get this vector that goes from P1 to Q? We'll call it V. Let's put it here. V. We'll call this blue vector here. We'll call this one B hat, right? Because it's the bisector of these two ends. And this will be n hat sub 0 and n hat sub 1. But we want to find Q. And you might say, well, we know that we want let's say we want a width of 20. So why don't we just go 20 times B hat? We just scale this one by whatever width we want. And that'll give us our vector from P1 to Q. The answer is, of course, it won't, because 20 is this distance here. The distance between the inside lines and the outside lines. But this distance is going to be longer than 20, because look at this. This is a fucking right angled triangle. So of course the hypotenuse is going to be longer than any of the sides. So you can't just scale it by 20. That shit will fuck you up eventually. So the question remains, how do we calculate Q? And we know, okay, we can't just multiply B hat by 20. But let's say we want to multiply B hat by some scaling factor. And we'll call that scaling factor K. So K, B hat, is equal to v hat, or v, just vector v. Vector v is equal to k times b hat. Now, what do we know about k times b hat? Well, we know that k times b hat dot, we'll just call this one n sub 0 hat. We know that the dot product, or the projection of this angle in this vector, is equal to 20, right? Because if we project this vector along this one, we're going to get the projection, which is the width here. So we know, I mean, okay, let me just, let me qualify that. We've got our vector here, v. We've got another vector going in this direction. Call it n sub 0 hat. Now, if we do v dot n sub 0 hat, what we're going to get is we're going to get the projection to here. It's going to be a scalar, so it's just going to be this distance. We're going to get this distance for n sub 0 hat dot v. And that's going to be equal to the width. We'll just define the width as w. So we know, all right, yeah, v is equal to some scaling factor times b hat. And we know that v dot n sub 0 hat is equal to w. We could use n sub 1 hat. It would be the same thing, but we'll use n sub 0. So what we want is we want to find k as a function of w, the width. So what we can do is we can substitute this into here, and we get k times b hat dot n sub 0 hat is equal to w. And then all we got to do is we do k is equal to w divided by b hat dot n sub 0 hat. And there you go. So you just do the dot product of b hat, this one, so the dot product of these two normals, and you divide w by that value. W being your desired width. It might be 20, it might be whatever. And that'll give you k. And then to find q, you just go q is equal to p1 plus, that's not a very good p, plus k times b hat. And that'll give you your vertex. And then you're done. And then you are done. And I mean done. So that is how we find our q's given our p's. So once we have our q's, then we just generate lists of vertices for our triangles. And we do the hokey pokey. We turn ourselves around, that's what it's all about. Yeah, so I think we're ready to get started. Now here's the thing. What we want to do before we actually make our triangle vertex extractor function extraordinaire is we want to, well, first burp, but then we want to ensure that all of our polycloses are clockwise winding. Because let me tell you right now, not all of the models that we have are clockwise. Some of them are clockwise, some of them are counterclockwise. It all depends on whatever vertex list my CAD program decided to spit out at the moment. So how do we ensure that we have clockwise winding? Well, there is a very neat function that we can do. I'm just trying to think of, well, let's make a private. Let's make a little private member function here. And we're going to call it bool is clockwise winding const. And this will just evaluate the current polyclose to see if it's clockwise. Now, how do we do that? How do we accomplish that? Well, there's a mathematical formula type deal that we can use. Let me just open up another project of mine because I already have that implemented in here. And it's very short, so I'm just gonna copy and paste it here. But I gotta find it first. There's my polyclosed is clockwise. So this is what we want. All right, area vertex previous. So we store the previous vertex. And we have the current vertex. And we calculate the area. Current x minus previous dot x times current y plus previous dot y. So we just keep going through all the vertices. So let me draw a quick little diagram here. So we step through all the vertices. So this is the previous, this is the current, and we do an operation, and then we move on. So this is now the previous, this is the current, and then we do the same operation, and then we previous the current, and we add up all the results of the operations between these vertices. And the result is something very close to the area. That was wrong. Where's my thing? Here it is. It's something similar to the area of the polygon. I think it's like twice the area or something. But yeah, you get that by the product of the differences in the x and the sums in the y. And that gives you something close to the area. Like twice the area or half the area, I forget, actually. But that's not important. We don't care about the area. The important thing is that it gives you the area, but if your thing is clockwise, it's going to give you a negative number for the area. And if your winding is counterclockwise, it's going to give you a positive number for the area. And all we want to know is whether the number is negative or positive. And that will let us determine whether or not our polyclosed is winding clockwise or counterclockwise. So it's just a basic iteration here through a container and performing an operation on pairs of vertices. So I'll let you copy this here. There's some math behind this. I think it has to do with triangles, but the area of a triangle or something, but I don't know. I really don't care, actually. All I care is that it gives me the proper answer. So yeah, we'll put this function into our polyclosed. And now, what we're going to do, so I'm going to look through here. look through my constructors. So we got two constructors. We got a constructor from initializer list and a constructor from file. And yeah, we'll do this. We'll do it for both. I don't care. Or I'll make a function. Yeah, I'll do that. Void make clockwise. So we do if is not, if not is clockwise winding. Now, if it's not clockwise winding, we want to reverse the order of the vertices. So what we're going to do... Why do I keep pushing this up here? I don't know. Whatever. Where's my other project? So I think I do that in... Fuck off, man. Where's my other... Where is my reverse? Okay, yeah, so standard template library gives us an algorithm to reverse a container, the order of that. We're going to use that. So we just do std reverse and begin and end. And I guess that works. Technically, we should probably include algorithm, but apparently it's been included somewhere along the lines. So make clockwise, and in the constructors then we just call make clockwise, and that will ensure that any polyclose that we load is now clockwise. Ribbed for your pleasure. Actually, that has nothing to do with anything. I don't know why that popped in my head, but let's try to build, make sure we didn't break it. We did break it. All right. Oh, I love it. I love it when the problems happen. You double click them and they take you into the template instead of into the place where the problem actually occurred. That's always fun. No operator found, which takes left-hand operator of constant vector. Yeah, I think we have to unconst this if we want to do that. Because if we don't unconst it, then we're not able to modify our vectors anymore. But as you can see, those kind of errors are the fun ones, because it doesn't tell you anything about what you actually have to change to fix the error. It sends you to a completely different place. And that is one of the risks of working with templates. They're not perfect. All right, so far so good. We've been able to load and get our shit clockwise. Now, we're gonna lose this triangle shit. We're gonna see, oh, fuck you. We're gonna see if everything still loads properly, even though we switched around a bunch of clockwise, counterclockwise stuff. And indeed it does still load properly. And the collision is still being handled correctly. So that means we're doing good. So far so good. Now it's time. Now it's time to actually create the triangle list. So we're going to create a new project. No, not a new project. A new item. A new file. A new class. New item. We want a header file. We're going to call this one triangle list. Yeah, I was thinking about making it a triangle list and then teaching you guys strips later, but I think I'll just talk about strips right now. That'll save us some time. I still want to get this episode done in under an hour. All right. So once we have our vertices, we're going to have to break them down into triangles to draw. So how should I do this? We'll call this one P. Fuck P's and shit. Where's numbers? 0, 1, 2, 3, 4, 5, 6, 7, and I think that's it. Yeah, 0 to 7. That's 8 vertices total. So in order to draw all the triangles, we would have to draw triangles with, we'll draw 0, 1, 3. And that would draw this triangle here, right? And then we might want to do, let's see, 0, 1, 3. No, fuck that. I misspoke. We'll start with 0, 3, 2. 0, 3, 2. And that'll draw this triangle. And the next one will go 3, 2, 5. 3, 2, 5 will draw this triangle. And then we'll go 2, 5, 4. 2, 5, 2, 5, 4, that'll draw this triangle. And then we'll go 5, 4, 7. So 5, 4, 7, and that'll draw this triangle. And then we'll go 4, 7, 6, and that'll draw this triangle. And then we'll go 7, 6, 0, that'll draw this triangle. And then we'll go 6, 0, 1, and that'll draw this triangle. And then we'll go 0, 1, 3, and that will draw the last triangle. Now, those of you who are, I don't know, astute, paying attention, not falling asleep, will notice a little pattern here. The last two numbers of a triangle and the first two numbers of the next triangle always match up. So we got 3, 2, 3, 2, 2, 5, 2, 5, 5, 4, 5, 4, 4, 7, 4, 7, 7, 6, 7, 6, 6, 0, 6, 0, 0, 1, 0, 1, 1, 3. Instead of specifying this triangle mesh as a list of triangles, 3 vertices each, we can specify it in terms of a triangle strip. And no, we're not talking about keep your dollar bills in your pockets here, gentlemen. We're not talking about that kind of strip. We're talking about this kind of strip. 0, 3, 2, 5. 0, 3, 2, 5. 4, 7, 6. 0, 1, 3. Now this is significantly fewer vertices that we have to store and manage than in this one, right? Here we got 3 times 8, 24 vertices. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. And how we then process this, we use a little kind of a sliding window approach. So let me get a new... So then we just slide this motherfucker along to figure out what vertices. So first triangle, 0, 3, 2. Second triangle, 3, 2, 5. Then 2, 5, 4. Then 5, 4, 7. Then 4, 7, 6. Then 7, 6, 0. Then 6, 0, 1. 0, 1, 3. And we're done. And that is the idea of the triangle strip. So triangle strip, you reuse vertices, and it's very efficient. And that's how it works in Direct3D and in OpenGL. Most meshes are specified in terms of triangle strips. You can also use lists of triangles, and they have their place, I suppose, but for the most part, using strips. There's another kind of triangle mesh type called a strip. No, did I just say strip? Fan, triangle fan. So in a fan, you start off with one vertex, and then you go along the edge of the fan, and it just draws triangles like this in a fan shape. So this would be 0, and then 1, 2, 3, 4, 5, 6, 7, 8, like this. But fans are kind of out of favor. They've been deprecated, so I wouldn't recommend using fans. I would say that strips are the way to go. So our little software system here is going to use strips. So that is why. I was thinking about maybe starting off with triangle list and then turning into a strip later, but that will waste time. Fuck wasting time. We want to make this go. I'm not very optimistic about our chances of ending this before the hour is up. But that's the way the cookie crumbles. You know, you got shit to explain, you got shit to do. You got triangle lists to code up in this motherfucker. So triangle list, it's going to be in some ways it's going to share things with the poly closed. Not much, but some. So we're going to start off, where's poly closed? I'm going to just copy and paste this here. I think I fucked it up. Yeah. That was not what I wanted to do. Delete all of my code. So we're gonna do, I can't do Control M, Control O because fucking my capture software is gonna, yeah. Collapse the definitions. There we go. So we obviously don't want a loader. And what else? Poly closed is not the name of our thing. It is a triangle strip. What else do we not want here? We don't want this DXL stuff, whatever it's called. Not important. Collidable circle, not important. Everything else, we keep it. Okay, now we're gonna go find and replace poly closed with triangle strip. Ooh, no, not entire solution. Whew. Dodged a bullet. Current document, thank you very much. There we go. Okay, so we've got a drawable triangle strip rasterize. Now the rasterization of the triangle strip is going to go exactly how I told you. We have a list of vertices. A color. I don't know about the color. We'll leave it in. Fuck it. And we want to draw triangles. So how are we going to handle this? We'll just do it the easy way, the pretty looking way. So we got our begin, we got our end. We don't need this -1 bullshit. Oh wait, we do. We want to go up to the end -2. Right. Where's my diagram? Yeah, because let's say our I this is I. This one right here. So we want that to be if end is here, we want end minus 2 so that I ends right here. We don't want I to go to here because you can't draw this triangle that doesn't have enough vertices. So we want to start here, end here, instead of ending here as we would normally end. So it's minus 2. Capiche? Look how nice I am explaining shit, man. I'm such a nice guy. Draw. Fuck. I need my IntelliSense, okay. Draw triangle. Okay, it exists. It is a thing. We need 3 vertices. So, the way we're going to do this, it's non-optimal, but I don't care. Trans times I plus 1 I plus 2. Yes. Next thing we want is clip and then color. So they're reversed, whatever. And parent dot color. Okay, why don't you like clip? Cannot be initial. Because triangle requires a. Not happy with that. Triangle wants a clipping rectangle. All right, you fucker. Rect I clip I equals. We're going to initialize it with clip. Good. So that will take this rectf clip and make it an integer clipping, and then we'll go clip I there, and everyone's happy. Okay, so we get I plus 1, I plus 2. Good. Okay. Now we're cooking with whatever we're cooking with. Some kind of volatile, flammable gas. Doesn't really matter what. Could be lighting your own farts, for all I care. Just I don't want to eat those hamburgers afterwards. Not interested in that cuisine. So we don't need this make clockwise bullshit because that's just not applicable here. We'll give the option of initializing our triangle strip with an initializer list just for testing purposes. But in general, we're going to initialize it from a polyclosed. Well, we'll see. We obviously don't need any of this bullshit. This is polyclosed bullshit. Get drawable is fine. All right, so I think this is actually going to work for us for our drawable. Color, it seems like we have the minimum here that we need to test out our drawing capabilities, which is the first step before we actually get to generating a wall triangle strip from polyclosed. So we're gonna, again, I can't do that. I wonder if Control E works. It does. Okay. So we comment out the stuff that does not matter. And we want to create, well, first we're going to have to include a triangle list. Oh, I called it triangle list, but it's actually triangle strip, so fuck me. Let's rename this bullshit before I start including. Rename triangle strip. I could go for a New York strip right now. Let me tell you, triangle strip. Strip. Now we need to give it a list of vertices. I think. So let's start off basic. We want. Why don't you like that even? Triangle strip is well, yeah. That's fair. I'm not going to fault you on that one, compiler. I may have had something to do with that. Triangle strip needs vertices. So we're going to go 0, 0. I'm building a triangle strip in my head as we speak. Feel free to feel amazed. Crazy, amazing, amazing, crazy, crying. All those good Aerosmith songs. Basically just the same song. What we want is, again, 0. And let's make one a little downside. We'll make this one halfway between on the x-axis. And in the y-axis, also, we're going to make it a little down. All right, here's a triangle strip. For all you kiddies. Why don't you like that? Well, okay. Fair enough. So we got a triangle strip. Let's draw it. We're going to do not camera, viewport. View? What did I name the... Oh, did I name it port? I did. Draw, because we don't want the camera to fucking start scrolling, and because we won't see our fucking strip. The camera's way out there in no man's land. Strip dot get drawable. Fuck that. Put our semicolons where they belong. And build. Prepare for errors. We're just going to put this in debug. Yeah, because I don't trust me. Oh, but it worked. Yeah, that's exactly what I would expect from my triangle strip. Again, with the error, fuck you. All right, let's add one more vertex to our triangle strip. And we're going to give it 200. 200. We'll do that. Build. That's about right. Let's add another vertex because I don't trust it. Wait, so it's this one, this one, this one, this one, this one, this one. So if we add one here, we'll get something interesting. So we're going to go down and to the left for the last vertex. Let's go down to 3, no, 100. And we're going to go down to 3, no, 400. You like it? You know you like it. Okay, you don't like it. Now you like it. Build. And there we go. That is our beautiful triangle strip abomination in action. Not much more to say about that. It works, and that's all we want. We got 10 minutes. Don't think we're going to make my original goal, but we're going to get close. We're going to create function. And it'll use an R value reference so that we can move vertices from one vector into another. So we're going to take std vector constant vec2 R value reference to movable, because this is a vector that we can actually take the contents out of and move it into our triangle strip. And again, we're just going to do the usual. We'll do that. Yeah. We'll also make it so that we can have the color here. Yeah, that's fine. Change that to movable. We're going to add a function to polyclosed. And it's going to return the std vector const and we're going to call this one extract strip why am I adding spaces? Extract strip vertices. And it's not going to change the current object. And here's where the magic is going to happen. Here's where we're going to do all that vector stuff that we talked about. So, I need a picture. I need a pretty picture. So 0, 3, 2. Is there any way I can get it to start here? I don't want I to start here. I want to start here.
A few moments later.
So auto previous vertex is equal to what? Star no and -1 or just back. Yeah, that's smarter. Why am I doing this weird? Vertices dot back. And then we go for auto I is equal to vertices dot begin end is equal to vertices dot end -1 because we don't want to hit the very end. We want to loop from here to here to here to the penultimate vertex. We don't want to loop to this one. That's a special case. We handled it outside the loop at the very end. Okay. Something's starting to come into form here. As long as I is not equal to end, I plus plus. Why is that an E? All right, so now we're looping through our vertices. Now we want to create N1 and N2. So we go vec2 or N0 is equal to star I minus previous. Dot, we're rotating counterclockwise. CCW90 dot normalize. Vec2 N1 is equal to star I plus 1 minus star I dot, again counterclockwise 90 dot normalize. So we got our two normals. Now we want vec2b is equal to n0 plus n1. Dot normalize. There's our B. Oh shit, we need a width here if we're going to extract the strip vertices. We need a float width. Make it constant. Just because. Okay, now we got our B. Let's take a look at our formula if I haven't erased it already. I hope I didn't erase it. That's not it. That ain't it. That ain't it. Keep going. Keep going. There we go. Formula. We calculate, first of all, we calculate K is equal to width divided by B dot N0. So float K is equal to B times N0. Good. I'll make these all const because I like const. Fucking love my consts. That's why I can't stand C#. Ain't got good const. The const is shit. All right, where's my thing? And then we want Q, the point Q, which is going to be our vertex, is equal to P plus K B hat. So const vec2 Q is equal to star I plus K, or is it the other way around? Yeah, it's going to be plus B times K. Just make sure that that's clear. We want to scale this one and then add it to our point. So now that we have Q, now we have to fucking do some stuff. Now how do we actually why do we actually order these vertices? We need first of all, we actually need a vector to put all this bullshit into. Vector const vec2. I don't know, output, strip. Yeah, strip is fine. All right, so this is always the part of the job I hate the most. Figuring out the order in which to put things. So I think we agreed it was going to be basically Q, then I. But then we fucking need the other one here. Jesus Christ. We haven't calculated this one yet.
2 hours later.
The order, it's driving me insane. All right, I figured it out. I'm going to change up our order of how we push these vertices into the vector. So we're going to go 0, 1, then 2, 3, 4, 5, 6, 7. So we push the inside, and then we push the outside. In, out, in, out, in, out. Anyways. So we start with I here, and this will be I plus 1, I plus 2, and we loop until I plus 2 reaches here. So we loop from begin to end minus 2. And then once we get to that point, we have to push the last ones just outside the loop. But you get the idea. So it'll go, 0, 1, 2, which will give us this triangle. And then 1, 2, 3, which will give us this one. And then 2, 3, 2, fuck you. 2, 3, 4. And then 3, 4, 5. And so on and so forth. So, yeah, let's get that all set up. So we don't need the previous thing here. I is equal to begin, end minus 2, and so forth. Now, initially we just want to push back. We're going to I. So the next function is the same as going I plus 1. I just kind of like the idea of next better. Maybe not. You know what? Fuck it. This will be easier for people to understand than, I guess, next and previous. So we push back I plus 1, which would be if I is here, I plus 1 is here, which is our start point, 0, in the triangle strip list thing. So push that back. Now we've got to find the our Q, quote unquote. So N0 is equal to, there's no previous, so what we want, we want star I plus 1 minus star I plus 0, or just I. That seems about right. There. We'll copy this one, we'll paste it into here. And now we want 2 minus 1, right? And that'll give us our two vectors n0 and 1, then it's normalize, find our k, find our q, and then we just push q back. So we just go push back q, and that's done. We just do that until we reach the end of our iteration, which is end minus 2. Right. Where will that take us? Let's go back here. So we'll iterate. The first one will go from, this will be I1, I2. This one will be I1, I2, then I1, I2. So we still have to handle this one and this one. Right. So, how are we going to do this? We could copy and paste. I'm going to open up a new scope in here so I can use my variables over again. And what we're going to do is we're going to copy this. So it's not going to be I plus 1. This one is going to be end minus 1, right? Or it could just be vertices dot back. Because that's the next one. This is the one we want to push. And then we got to calculate. So what is this going to be? So I plus 0 my brain is starting to freeze up again. This is I, this one, this one, this one, and I is here, this one, this one, this one. I is here, I is here. Next one, I will technically be here. So that's end minus 1, end minus 2. So So we want vertices dot end -2. -2. And this one will just be vertices dot back. And here's vertices dot back, and here's vertices dot front. All right, so far so good, I think. And now we just have our referencing our earlier variables. I is, wait a minute, this is wrong. Oh, I found a mistake. This should be I plus 1, right? Because, like in the beginning, this would be I, but we want this one here, so it's I plus 1. And then we add our vector q to that. So it should have been, ooh, caught a break there. So this should be I plus 1, which is vertices dot back. Good. Next, and the last one we're going to do here is we're going to push back vertices dot front. So I plus 1 is now front. I is back. So we have I plus 0. This should be back. Get rid of that there. Just a whole bunch wrong with this this statement here, but we got that done. So back is 0, right? Is I. And this one should be front. Right, because now we're working with these vertices here. So its front is here. This is back. And this one's going to be, so this is I plus 1, I plus 2. So I plus 2 is going to be vertices dot begin plus 1. And that's iterator, so we got to dereference that there. And this one is I plus 1, which is vertices dot front. And that's fine, and that's fine. And Q is going to be vertices dot front plus BK. And that should, I think we might be missing a few vertices still. For this one. Let's take a look. So let's see if I can't undo my way out of this bullshit. More undo. Undo more. We're getting good. All right. No, I want to keep those numbers. There we go. All right, so if we push them back in order, 0, 1, 2, 3, 4, 5, 6, no, 6, 7, we get 0, 1, 2, and then we get 1, 2, 3, and then we get 2, 3, 4, and then we get 3, 4, 5, and then we get 4, 5, 6, and then we get 5, 6, 7. So we're still missing 2 triangles in here. So we need to push back. We want 6, 7, 0. So we need to push back 0 and 1. So basically we just got to copy the first 2 into the back. So once we're done there, we go strip dot push back. Strip at 0 and strip dot push back. Strip at 1. Now it could be said that I made this more difficult on myself by using iterators, where I could have used I could have just looped through it with indexes and used like indexes like 0 and 1. And that's true, but there are good reasons for using iterators. If you use iterators and then later on you change your container to a list instead of a vector or whatever other kind of container, you can keep most of your algorithms because iterators don't care about that kind of stuff. And the other thing is, well, I mean, this +1 and +2, that wouldn't work with a list. I'd have to use next and previous, but you get the idea. And the other thing is, I think it's just good to get practice working with iterators because they're important. They're an important concept to master. So I'm giving you guys practice. But yeah, this should give us our triangle strip if I didn't fuck anything up, which I quite possibly have done. But we get all of the vertices except for the last 4 here and then the last 2 that have to be repeated. So most of the work is done in here, of course. And in here is the last little bits of cleanup. And then finally, return strip. Let's try and build this. Cannot convert from initializer list to triangle strip. Is it because I added this? Probably is. No, I can't. You can't just comment that one part out. You gotta comment the whole thing out. All right, let's try it again. Yeah, it builds. Well, fuck, now I've got to think. It's probably because it can't tell whether to use the initializer list or whether to use this thing here. Well, fuck. We don't really... Yeah, we do. Okay. No, we don't need this. I did it again. I am not really interested in getting to the bottom of why this is... why this isn't kosher. I can't have both of these going at the same time. But it's probably just I can't tell whether to use that... I can't tell whether to use this initializer to initialize a vector or to initialize thing. I don't know what it is. It's fucked up. It's pissing me off. Doesn't matter. Doesn't matter. All we got to do is generate. First, we're going to create a polyclosed. And we'll call it polyclosed P. Let me see what kind of... yeah, I got an initializer list on this one too. So we want to create a box like we had before in our test. So we're going to go 50-50. Fuck. We need more. Need more curly braces. Let's keep it coming. What else we want? So we'll do a 50-50, and we're going to do 150. Then we're going to do 100, 100. And then we're going to do 50, 100. And this should give us a nice box, polyclosed box. And then we're going to create a triangle strip based on p.extract strip vertices with a width of 10. I'm going to call the triangle strip by its name. And this should, well, at least it'll compile. It compiles. Now, can we get this motherfucker to run without... Probably not. It's probably going to be bad. Yeah, it's bad. But it didn't crash. Which is, I guess, something. Alright, so extract strip vertices not really doing it for us, is it? Alright, let's just debug this motherfucker. We'll end this lesson with a bit of a debugging, a little debugging corner here. Step in, step out, step in, step out. Ugh, I hate you. I could have set a breakpoint somewhere else, but I didn't. Okay, so let's go debug. Let's get our windows up in here. All up in this motherfucker. And what do we got? So we got our vertex list. Don't care. Vertices. 50, 50, 100, 50, 100, 100, 50, 100. So that should be clockwise. So let's step in. Is not counterclockwise. Okay, so it passed the counterclockwise test, which is good. So our polyclosed is as it should be. Our input, there shouldn't be anything wrong with it. Now we just got the problem of stepping into extract strip vertices. So we got our strip. We're going to push back I plus 1. So where's strip? Why is it 0? Okay, yeah. Item 0. Size is 1. So we've got 50, y 50, x 100. And that is the proper vertex. Let's see if our calculations hold. So N0. N0 is giving us a normal vector which is pointing in the negative y direction, which is correct. Because, let's just visualize here for a second. Our box. This is the vertex that, or this is the normal that N0 should be. And that's the normal that we're getting, so we're good. So far, so good. Let's keep going. To thrust. Step over this one. Here we're getting N1 is positive 1, negative 0, which is also correct, right? Let's go back to our drawing. My name is Simon. I like to do drawings. So yeah, this is the one we want. That's the one we're getting. So far, so good. Let's continue. B is equal to positive 0.7, negative 0.7. This is also correct. We want a positive y and a positive x. Or I mean a positive x and a negative y. So like this. And K is equal to 0.7. Ah, herein lies my dumb bullshit that you can all, laugh at me for if you want. It's fine. I kind of forgot that we have to divide width by this bullshit here. Otherwise, we're not getting anything. So we're going to divide width here. And we're going to have to do that everywhere else. So K is equal to that. K is equal to that. And that's it, I guess. All right. Well, that was fun, wasn't it? Let's see if that is the only error we have. Fuck you. Show me. Oh, yes. And we have action. All right. So this is good. We are getting somewhere here. Now comes the moment of truth. It's passed the test of our very simple polyclosed. Can it extract the vertices from a full-fledged map? So what we're going to do, so we're going to go Control U. All right, we're going to uncomment this. What do we got here? Okay, so we got to change map. We don't want a polyclosed model. We do want polyclosed model. Well, actually, we want polyclosed boundaries. Because the polyclosed, we still need to keep that for the collision detection. But we also want triangle strip model. All right. Now, handle collision is going to be boundaries.handle collision. And this one is going to be model.getDrawable. Why don't you like it? You should love it. Still not loving it, huh? Okay, what's the problem? All right, okay, so it's polyclosed model. It's got to be triangle strip. That makes sense. I endorse this. And now we create the model from the file name, and then we got to create... No, wait, we don't create the model from the file name. We create the boundaries. Then we create the model from the boundaries. So boundaries dot extract strip vertices. And we need a width for our const float wall width is equal to, I don't know, 40. Is that too thick? I don't know. We're gonna see. Make it 20. Play on the safe side. And we'll just put in here wall width. How's that? Likes it just fine. And that should be all that we have to change. And there we go. We have got walls with width. We've got girth to them. You can't handle the girth. Actually, they're a little thin. I think we could get a little girthier on these walls. Let's try 50. Let's try good 50. Start debugging. Oh yeah, look at that. That's some fat walls right there. Actually, they're kind of clipping into each other. Too fat. The walls are too fat. Try 40. The walls are too fat. There we go. That's good. All right, here we go. So that is that. It looks good. I like it a lot. And that is how you use vector math to manipulate your geometry, to generate new geometry. And that's how triangle strips work. And That's where babies come from, basically, is what I'm trying to say. So, yeah. Now, a couple of things I want to talk about quickly here. I won't take much of your time, but we've got important business to discuss here. Business item the first is, I got a challenge for you guys, for those of you who really want to take it to the next level. So we've got a system where we can generate a triangle strip from a polyclosed. I want you guys to generate a triangle strip, or actually you probably need multiple triangle strips, but I want you to have an algorithm that can take a polyclosed and generate triangle strips such that you can render the object solidly. So for example, the ship, we have a polyclosed for the outline of the ship. And instead of generating a wall around that, I want you to generate triangle strips such that you can draw a solid ship. Now this is what I have. Let me just show you quickly. If I can find the motherfucker. That's not it. That's not it. I might not be able to find it. Oh, I found it. No, that's kind of not really what it is. Thrust folder. Not happy about that turn of events right there. Let's just pretend that never happened. So yeah, what you got here, that is, you didn't see that. You didn't see that. Let me just go branches here. Jesus Christ. Okay. Fucking changes, man. What branch am I even on? I gotta figure out what branch I'm on. What branch? Rotska. Okay, that's the right branch. Changes. Fuck you, git. And now I can change my branches. Starfield. All right, good. So here's the thing I wanted to show you before I was so rudely interrupted. See here, we've got a ship and it is filled. The ship is full. See that nice filled in ship, not an outline. That is what I want you to be able to generate. Just make sure I'm not closing the wrong thing here. So you need an algorithm that can turn an outline of something into a solid triangle mesh consisting of probably multiple triangle lists. Because you can't generate, a mesh for any given object with only one triangle list. You generally need more than one strip. Not list, strip. I meant to say strip. So that's my challenge, and it's not an easy one. That is a difficult. If you thought generating this wall was difficult, that's baby. That's baby's talk, play kind of thing. That's child's play. That's the word I'm looking for. Child's play. Like with that creepy mannequin. So what you need is you need to be able to generate this, and it's going to be hard. So it's a challenge. It's not like, if you can't do this, then I hate you forever. It's like, if you do this, then you will have my grudging respect. So, write a routine that can generate a mesh based on a polyclosed. And then, let us know on the forums, and I will give you a shout out because, hey man, that's good shit. So that's the challenge. The next thing I want to talk about is about the future. About the future of the tutorials. Because we're nearing the end of the advanced series. Or possibly the end of the advanced series. There's only one more topic that I have to cover, that I want to cover, and that's basically it's texturing. It's kind of like that thing that you sort of just saw a peek of, that rotating bitmap, and that's what we're going to be covering. That's going to be the last topic, the last mandatory topic for the advanced series. And when that's finished, I am going to have a poll on the forums, and I'm going to ask you guys, do you want me to continue with the advanced series, or do you want me to move on to 3D? Because after we cover texturing in 2D, we will have basically all the tools that I wanted to develop so that we can start on 3D. So the option is going to be start on 3D immediately, or cover other topics in advanced 2D, such as bloom, which is that glow effect that you saw, such as particles was another one that I was thinking of. Particles. And inside of these topics, like inside of bloom, there are things we could cover like SSE and multi-threading. And what else? Besides covering, technical topics, things we could also do is develop a game, make a game out of this. I was actually thinking about making the engine that we've been developing, the thrust engine, into something like a rock and roll racing game, which is a combat racer, but in space. So these are some things that we could do in the advanced, and I'm going to have a poll, see if you guys want to continue on, what you're interested in, or if you just want to jump to 3D and forget about this, or maybe pick it up later. But that's for the future. First thing is we got to get done with texturing. And that's going to take a bit. It's probably going to be two episodes. So maybe 4 hours in total for texturing, because it's a big topic. And when we're done lesson 12, then we can either continue on or we can go to 3D. But that will depend on you guys. I'm going to make this a democratic process here for once. This is still a dictatorship, but sometimes I like to throw the plebs a bone. You know what I'm saying? Anyways, that's for the future. For now, I want to see someone rise up to this challenge and create a mesh generator, a polyclosed to mesh converter. I've already done it, so I know it can be done. It's not going to be easy, but it will be rewarding. It's an important skill. Because all this vertex manipulation and geometry manipulation, that doesn't go away even when you do 3D, hardware 3D. You've got geometry shaders. You've still got to manipulate vertices and do it in a vector math-oriented way. So I'm teaching you the skills that will be applicable in the future. So let's see. I'm waiting at those forums, and I want to see someone rise up to this challenge. But until next time, that's Chili signing out. Happy coding and good luck.